Chemistry 30, Acids and Bases. This is lesson 3 that goes along with the AB2 assignment on calculating pH for strong acids, strong bases, and weak acids. Strong acids dissociate 100% in water, so the H plus will equal the labeled concentration of the acid. Strong acids can be identified on the data table as those with very large Ka values and a one-way arrow. What is the pH of a solution that is 0.25 molar HCl? First off, how do I know this is a strong acid? Well, I go to my green sheet and I see that HCl is listed with a one-way arrow. How many strong acids are on our green sheet? We have 6 acids with one-way arrows. So if we are asked a question about any of these acids, we will treat it just like this example. I write my balanced decomp, which I took from the green sheet. HCl is 0.25, and since it dissociates 100%, 0.25 HCl's make 0.25 H pluses and 0.25 Cl minuses. So the H plus concentration is then 0.25. To find the pH, I take a negative log of the H plus concentration. And negative log of 0.25 is 0.602. So the pH is 0.60. Strong bases are a combination of lithium, sodium, potassium, rubidium, cesium, strontium, and barium mixed with oxide, amide, or hydroxide anion. They also dissociate 100% in water. Amide and oxide anions produce hydroxide by reacting with the water. Now that's a lot to remember, so don't worry, you don't have to, because it is on your pink sheet in the bottom left-hand corner of your periodic table. So amide, as mentioned at the end of that note, will react with water to produce hydroxide and ammonia. So when we do our decomposition reaction, whatever the amide concentration is, that's what our hydroxide concentration will be, and then we can find pOH. If oxide is produced when the salt is dissolved in water, an oxide reacts with water to produce 2-hydroxide. The oxide itself picks up the H plus, turning itself into hydroxide, and when it steals the H plus from water, it turns water into hydroxide. So when we do our balanced decomp reaction, whatever the oxide concentration is, we double that, and then we have the hydroxide concentration. And once we have that, again, we can then find the pOH. What is the pH of a 0.0024 molar NaOH solution? This is a strong base, so it dissociates 100%. So if I have 0.0024 molar NaOH, that makes 0.0024 molar sodium ion and 0.0024 molar hydroxide ion. So since the hydroxide concentration equals 0.0024 molar, I can then find the pOH by taking the negative log of that concentration. So the pOH is 2.6198. Now to find pH, well, we know pH plus pOH equal 14. So 14 subtract the pOH will give me the pH. 14 subtract 2.6198 gives me a pH of 11.3802. Corrected to 2 significant figures would be 11.38. 2 decimal places in the pH scale gives us 2 significant figures. What is the pH of a 1.5 molar strontium hydroxide solution? It's a strong base, so it dissociates 100%. If the strontium hydroxide concentration is 1.5, then the strontium concentration will be 1.5, but the hydroxide concentration will be 3.0. And that's because each strontium hydroxide that breaks up produces 2 hydroxides. So the hydroxide concentration is 3.0 molar, and knowing that, I can find pOH because pOH equals negative log of the hydroxide concentration. I sub in the concentration of 3.0, and the pOH is equal to negative 0.477. Now pOH plus pH equal 14. So to find pH, I will subtract pOH from 14. 14 subtract negative 0.477 gives me a pH of 14.477. Corrected to two significant figures is 14.48. What is the pH of a 1.20 molar strontium oxide solution? Well, again, strong base dissociates 100%. And if I have 1.20 molar SRO, that gives me 1.20 molar strontium ion and 1.20 molar oxide ion. So the oxide concentration is 1.20. But we said for every oxide released into water, it produces two hydroxides. So the hydroxide concentration will be double that of the oxide concentration. So my pH will be negative log of the OH minus concentration, which is 2.40. And that gives me a pOH of negative 0.3802. Again, to find pH, I will subtract pOH from 14. And that will then give me 14.3802, corrected to three significant figures, is 14.380. Three significant figures, 3 decimal places in the pH scale. As earlier stated, weak acids are in equilibrium, and we need to use the ice chart to determine the proton concentration when the acid is dissolved. So we will reference our green sheet. Weak acids are the ones that have the two-way equilibrium arrow. The equilibrium constant for acids are found on the data table as a Ka value. The larger the Ka value, the stronger the acid. Example, calculate the pH of a 0.50 molar CH3COOH solution. So I go to the green sheet and I look up CH3COOH and I write down the formula I find there. Then I write ICE. Initially, my CH3COOH is 0.50 molar. I won't have any CH3COO minus initially present. And my H plus concentration is going to be 1 times 10 to the negative 7. That's because distilled water does have a pH of 7. Thus, the proton concentration before adding anything should be equal to 1 times 10 to the negative 7. Often we're tempted to put in a concentration of H plus of 0, but that would mean that we have an extremely basic solution. Because if we have no H plus, we've got to have a lot of OH minus. Our change, well, since we have a 0 on the right-hand side, that means our right-hand side has to go up. And if our right-hand side goes up, the left-hand side must go down. And at equilibrium, we just merge all those values. So I write my equilibrium expression, but note instead of writing KEQ, I write KA, and that's because this is an equilibrium constant for a weak acid. When I sub my numbers in, well, I'm going to take the values from the equilibrium line, but I wrote my Ka as 1.8 times 10 to the negative 5. And why would I do that? Because on the green sheet, it said that for acetic acid, the Ka value is 1.8 times 10 to the negative 5. Now I will multiply both sides by the denominator. So on the right-hand side, 0.5 subtract x will factor out. Then I'm going to distribute 1.8 times 10 to the negative 5 into the brackets, and I'm going to distribute x into the brackets on the other side of the equation. Now I'm going to move all my terms to either the left side or the right side. I'm going to move them all to the right-hand side because I like to keep my x squared term positive. So I will add 1.8 times 10 to the negative 5x to both sides, and I will subtract 9 times 10 to the negative 6 from both sides. And that will give me then 1x squared plus 1.81 times 10 to the negative 5, subtract 9 times 10 to the negative 6. Of course, that's all equal to 0. And now I've got an A value of 1, B value of 1.81 times 10 to the negative 5, and a C value of negative 9 times 10 to the negative 6. Pop that into my quadratic equation, making sure that I double bracket the bottom, the entire top, and everything underneath the square root sign. So that's 3 extra sets of brackets. I punch it into my calculator, and I get x is equal to 0.002990963. Since I'm looking for pH, I'm going to have to find the H plus concentration. And the H plus concentration in our equilibrium line is 1.00 times 10 to the negative 7 plus x. And that is going to then give us 0.00299163. Now that I have the H plus concentration, well, pH is just negative log of the H plus concentration. So I will sub that number in, and I wind up with a pH of 2.52. And that is the end of the lesson. You are good to start working on this extremely long assignment.